In this video, we're going to learn how to calculate the slope at a point along a polar curve. And where our story begins is to remind ourselves how we computed slope of a parametric curve. So if we have a parametric curve where our parameter is, say, t, we noted that, well, if we're interested in slope, slope is still a rise over run. And in particular for us, it's a dy over dx, a change in y over change in x, or rise over run. And for a parametric curve, we found this to be a dy derivative with respect to t all over dx dt. And the reason I bring this up is, even though this is a slope of a parametric curve, we're going to extend the idea of our parameterized curve for our polar curve. So the second thing we'll do is parameterize our polar curve. And this sounds a bit complicated, but remember, if we're given a polar curve, say r is equal to a function of theta, there's a few things that we know about polar curves or polar coordinates and Cartesian coordinates. If we go back to our translation equations, or our transformation equations for that matter, we know that x, well, that's always equal to r cosine of theta. And y, that is always equal to r sine theta. And remember, what we're trying to do is parameterize our x and our y. So on this right-hand side, if we just get all functions of a parameter, we could parameterize x and y. And welp, we're just about to do that. We know that r is always equal to f or some function of theta. That's our polar curve up here. We can substitute that into our transformation equations. So we have that x is equal to, well, whatever that function of theta is, our polar curve, times cosine of theta. And y? Well, y is whatever that polar curve is that we're given, times sine of theta. So what this gives us are two parametric equations, x and y, in terms of theta. So we have that x of theta is equal to, well, whatever polar curve we're given, that's that f of theta. Let's just highlight that in blue. Times cosine of theta. And y of theta, well, that's just going to be the curve that we're given in the problem, f of theta times sine of theta. And once we have done this, we have a set of parametric curves now. And then we can hit this with all of the parametric calculus that we've already done. In fact, we could go all the way back to step 1, or our first thing we did, except instead of taking derivatives with respect to t, since our parameter now is theta, we just have to find the slope by taking dy d theta all over dx d theta. So let's go ahead and do an example of this. In this example, we'll find the slope at a specific point along a polar curve. And let's use the polar curve that we just sketched in the last video. R equals 1 plus sine of theta. So again, what this means is we're handed this polar curve, r equals 1 plus sine theta. We're told what point we care to calculate the slope at. So we can go ahead and parameterize and then use what we know about parametric calculus. So I'll say step 1. This is really just a reminder, we need to parameterize this first. We always know that x is equal to r cosine theta. And in this case, well, our r, that's just equal to 1 plus sine theta. So x is equal to 1 plus sine theta times cosine. Again, 1 plus sine theta, that's our r. We can do a similar thing for y. That's coming from our other transformation equation. R is equal to, or y is equal to r sine theta, which is 1 plus sine theta, that quantity, all times sine of theta. Again, because that is r times sine theta. And in this problem, we are told r is equal to 1 plus sine theta. So we have our set of parametric equations now. X and y are both functions of theta, so we can go ahead and calculate the slope. So dy dx, since we're in this parameterized polar setting, it's now the derivative of y with respect to theta all over the derivative of x with respect to theta for our slope. And well, you might see what's coming here. We're just going to get to do a bunch of product rules. Let's take the derivative of this second equation first and compute dy d theta. So if we compute the derivative of the first piece and multiply by the second piece, well, that'll give us derivative of 1 plus sine is a cosine. And then we multiply by the second piece, which is just that sine. And then we do the opposite. Take the derivative of the second piece and multiply it by the first piece. Derivative of sine is cosine, and then we multiply that by what that first piece was, 1 plus sine theta. And we'll divide that by the derivative of x with respect to theta. So let's look at that second equation now. So looking at the x equation, we'll take the derivative of the first piece, derivative 1 plus sine theta. Again, that gives us a cosine. And then multiplying it by the second piece, which, well, that's our cosine again. So we get cosine times cosine. And by product rule, we now do the opposite. Take the derivative of the second piece, which is that cosine, and then multiply it by just that first piece itself. So derivative of cosine, that's minus sine, and we multiply that by 1 plus sine theta. And that is our slope. And again, this slope is dy dx, rise over run, but it's all in terms of that parameter. In this case, it's the parameter theta. So we can go ahead and simplify just a little bit. In that numerator, we will get, I guess it looks like, after a lot of simplification, 2 sine theta cosine theta plus cosine theta. And then we divide that by cosine squared theta minus sine squared theta minus sine of theta. And what we care about is this derivative evaluated now at pi. So let's plug that in. Or essentially, evaluate both sides at pi. So if we evaluate this derivative now at pi, we have 2 times the sine of pi times the cosine of pi plus cosine of pi all over cosine squared of pi minus sine squared of pi minus sine squared, or sorry, minus sine of pi. And well, sine of pi is equal to 0. So a lot of terms just become 0 here. So let's go to the next page. So what we have left is, well, a cosine of pi in the numerator divided by a cosine of, or cosine squared of pi in the denominator. And that was when we found the slope dy dx, and again evaluated that slope at pi. And this whole quantity again comes out to, well, 1 over cosine of pi. Cosine of pi is -1, so this slope just comes out to -1. And just to reiterate this entire process, when we're interested in finding the slope along a polar curve at a particular point, the first thing we need to do is parameterize that curve. Whatever is our polar curve that we're given, in this case it was 1 plus sine theta, we're just going to plug that into our r when we take x equals r cosine and x equals r sine. And then we just, of course, once we have that parameterization, we can just hit this with the parametric calculus that we've already developed in this course.